So we have started friction factor, deriving friction factor for flow in tubes. And just to quickly recap, what are the friction factors for? They're actually for generalizations, or they're used for upscaling. And not only upscaling in terms of porous media upscaling, which is complicated geometry upscaling, but also flow regime upscaling. So for laminar flow, we have analytical formulas for flow in tube, assuming the tube is long enough and all that business without end effects. But we do have actually very good operating formulas that we can work with. Similar is true for a lot of geometries with a constant cross-section. But all of those are valid in laminar flow. And the moment I start departing from laminar flow and having larger velocities, that's going to change. So Reynolds number is something that basically it takes into account both shape and the fluid viscosity and the velocity, or dominant velocity in the system. And that's a dimensionless number that actually governs what flow regime you may need. And often when I'm solving, I have this cat and mouse problem because, or chicken and egg, however you want to call it, because in order to solve for flow, I need to know the flow regime. But I need to solve for flow to know the flow regime, right? So there's this. So sometimes you actually have to assume certain equations and certain flow regime, get the expressions, then check that actually your Reynolds number matches what you assume. And if not, then you move on and go. So we're gonna, and friction factors actually come in handy for that type of examination. So we're gonna have an example. So second part is that we want to do generalization, and we want to actually relate things to experiments. So we will define friction factors, and we will use guiding lights that we will use is that we want to interpret them in terms of quantities that we can actually measure. And then I can do an entire series of experiments in tubes. That's not a problem. And I can give myself engineering formulas that work very well for all kinds of tubes. And that's an important thing. Tubes might be simple, but tubes are also everywhere, of all sizes. From our little rocks and small micromodels to, Alaskan pipeline. That's one big tube. When I was standing next to it, it was kind of starting here on the so it was basically twice my height. Overall, the structure was propped up, but overall structure was about twice my height. So it's not a joke to flow through that tube. Right? And the formulas for turbulent flow are definitely useful. And that's where we can actually use friction factors. So without further ado, let's just briefly review what we did last time. So what we looked at is, okay, how am I going to define friction factors so that I can go and measure things using it? I'm going to start with something I know and in laminar regime, and that's going to be my basis, and then after that I'm going to adjust as necessary. So for flow in the tube, we can evaluate what is the viscous part of the force that fluid exerts on the surface. We know how to integrate shear stresses, speaking of my talk about shear stresses. So essentially, this formula evaluates to P0 minus PL, which are my generalized pressures at the end of the tube, n times area, cross-sectional area of the tube. And we notice that actually by integrating the viscous stress on the surface, it's actually balanced with the pressure forces at the ends of the tube. Okay. So, fine. So this is my, what I call kinetic force. And then I'm going to try to relate this kinetic force to some characteristic area A, kinetic energy density, some sort of averaged kinetic energy density of the fluid, n times F. F is going to be this friction factor that is multiplying A and K to get us the force. Okay. So that gives me F as Fk divided by AK. And that is equal to, so based on these calculations, my A, my characteristic area is 2PRL. I had it right here, and K. And my K is 1/2 rho average V squared. So that evaluates to so R over L, 2 times 1/2, pressure difference divided by rho V squared. And sometimes they actually do leave 1/2 over here, because that gives me idea that it's average. So kinetic energy is 1/2 mv squared, right? So kinetic energy density is 1/2 rho v squared. So that's just and then I have to just have a multiplication 1/2 here. And this is what we actually define as so-called fanning friction factor. Let me see. Yes? The number before R over L, it should be 1/2. 1/2. Because I have 1/2 in my... So that is fanning, and sometimes it's also expressed in terms of diameter of the spheres. See, so rebooting the machine helps in my touch screen this time. And I'm going to put VZ just to make sure that it's axial velocity along the tube. And this is so-called fanning friction factor. And it's a dimensionless quantity. And I can measure everything in there, right? So everything that I use to compute it is measurable. Average velocity is literally from measuring flux coming out of the tube. If I can't measure that in my experiment, well, I don't know, maybe I shouldn't do experiments, right? So that's one thing I can measure. So this is a definition of friction factor in tubes. So this is in tubes. Do not use this for any other geometries. Now let's actually see, for this being a tube, if I actually have laminar regime. I know VZ using the formula. So I can remind myself chapter 2 in BSL. It's actually P0 minus PL times R squared divided by 8 mu L. So basically, when I take a look at my friction factor again, I'm going to basically express, so I have VZ here that I can plug in, right? Or I can, let's see what is faster quickly. It is better to actually get rid of the pressure. So I'm going to express this and plug in. So when I do that, this is 8 nu L Vz divided by R squared, which is 1 over 4d squared. So I just plugged in for R and times 1 over 1/2 rho Vz squared. So when I clean that up, I will actually get, this is 2, 8, 8, 4 and 4 will go away to 16, that is correct. 16 mu divided by d rho Vz. Does anything jump at you? Reynolds number. Okay. So Reynolds number is defined with diameter, rho, average velocity or some sort of characteristic velocity, and mu. And this is actually what I see is 16 over Reynolds number. Okay. So I can recognize one over Reynolds number. So basically for laminar flow regime, I got that F is a function of Reynolds number, and that specific function is 16 over Reynolds number. Okay. So this is for laminar regime. And in tubes, that's typically, we said when Reynolds number is less than 2100. So what this says is essentially that my friction factor, according to this relationship, at least for laminar flow, it indicates that friction factor might be the same for the same type of flow regime. Okay. So friction indicates that friction is same for what we call similar flows, or similar flows, flow regimes. And that is powerful, right? We already know how my Navier-Stokes behaves in that sense, and that I can solve for the same flow regime. I solve things only once, and then I just scale them appropriately, because I can rescale Navier-Stokes to have dimensionless quantities, and that's where actually Reynolds number shows up, multiplying, I believe, that velocity, the nonlinear velocity term. So it's good that actually this seems to hold for friction factors as well. Now, we're not gonna do the derivation for the turbulent flow. What can go into analysis of the turbulent flow? But basically, what's done is that experiments are done. I can measure friction factors for experiments based on that fanning friction factor, right? So I can basically compute what that friction factor is, and I can plot it against Reynolds number and see what this relationship could be for different flow regimes. And that is the formula that I have, or that is the graph that I showed you last time around during the introduction. So basically, I plot friction factor as computed by fanning formula, and I plot it against the Reynolds number, this part I do get laminar and I get pretty good agreement. No problems in laminar flow ever. Here, the points are not shown, so we gotta trust them that these are basically curve fits. What you see here are curve fits to experiments. So the procedure is, okay, derive the heuristic and prove it to yourself that friction factor indeed is something that is a function of the flow regime, and then do a host of experiments to actually get these relationships, and then those are the working relationships you can use for tubes of all sizes. Okay. That is essentially how it's used. So one could, again, one can look theoretically into turbulent flows, which we are not going to do, but you have that in chapter 6 if you'd like. And also find that to a pretty good extent, friction factor is a function of Reynolds numbers for turbulent flows too. We didn't do that because we never actually went into deriving relationships for turbulent flow. So then in practice, F is measured based on the experiments and plot / curve fit against Reynolds number. And you can see figure 622 in BSL for that. That's the one that I flashed. And those are then the operating formulas we use. All right, let's take a look at what do we get around sphere. So again, I know my formula Fk is AKF. So that's what I'm going to use to define the friction factor. I just have to agree on what is my A going to be and what is my K going to be. Okay? So if I have flow around the sphere, right, we typically look at the sphere, and then there's this far field velocity. If you don't have the sphere, you have this velocity V infinity, right? And then you place sphere in there and you're looking at the disturbance of that velocity, but otherwise it was constant before. So that's a good choice for my kinetic energy density. That's something that I measure far away from the sphere. So this is a no-brainer. It's going to be 1/2 rho V infinity square. And area that we're going to use for the sphere, one could use area of the entire sphere, but not all parts of the sphere are really playing that much role in providing resistance to the flow. So what's most of the time, and also I don't always have spheres. In practice, I will have objects that are a little more complicated. So instead of looking at the actual surface of the object, okay, I'm going to actually look at sort of the projected area as I'm flowing to. Like I see R square P as a projected area. Because if I'm measuring particle sizes, that's typically what I'm measuring. If I have a sieve, that's what I'm measuring. Okay? So that's a better sort of or more realistic area to take from the measurement perspective. If I just have spheres, sure, spheres I know everything analytically. But in reality, I have some sort of grains, and those grains I typically measure their sizes and diameters using a sieve. Okay? So I kind of measure their projected area or what passes through the sieve at certain angle. So what's taken, so basically what we agree is area is projected area onto plane perpendicular to velocity. Okay. And I know what is my Fk. So Fk, I do have formulas, but one thing that is easier, so I could go into entire integration exercise, but what is easier to measure is typically terminal velocity of the sphere falling through the fluid. So we're going to express that force from that balance. So basically, in terms of measurements, note that it is easy to measure terminal velocity of a sphere falling through fluid. So let me quantify easy. You also have to make sure that that sphere is not rotating or doing anything funny, that it's actually just moving like this. So in theory, relatively easy. In practice, I assume that there's quite some fun making sure that that sphere is actually falling nicely without doing anything else funny other than just falling down, right? And when it actually finds this terminal velocity at which it's not accelerating anymore, I know that I have force balance, and that's basically a force balance between gravitational and buoyant force. So in that case, that's balanced by this force of the fluid on the sphere. So that's gravitational minus buoyant force. Gravitational force is simply the volume of the sphere. And I'm assuming some solid material. I'm going to say rho s g. So mg, really. Minus buoyant force is the basically gravity of the displaced fluid. I'm going to put that as rho f g. So when I put that in the formula, I get that my F is this Fk. And now my V infinity will be replaced with that terminal velocity. So I kind of flipped the reference systems. In our general analysis of the sphere, I have fluid moving around the sphere. In this case, it's actually I have sphere moving, and the fluid is technically static, at least far away from the sphere. So who is moving depends on where you're sitting, on the sphere or outside of the sphere. So basically that gives me friction factor definition for a sphere. I'm just going to rewrite it slightly differently and clean it up a little. My friction factor is 4/3. I'm going to use diameters again because that's what we typically measure for particles. Rho s minus rho f divided by rho f. So what I'm going to do in the lab is I'm going to measure terminal velocity of a sphere falling through fluid without doing any funny rotations or anything like that, just falling. And I'm going to see where it achieves terminal velocity. That's the Vt I'm going to plug in here. I know the diameter of that particle B, and I know the density and densities of both solid and fluid. All right, so let's actually now use this before we move on to sphere packs. Trust me, sphere packs are so much fun. If you take carbon-Quaternion derivation and make it about 3 times worse, we're going to get friction factors. There's a whole lot of twists in defining. This is 6. I need to open. 7. So let's do an example where we're going to use friction factors. What is the terminal velocity of a viscous heavy oil droplet of density 0.95 gram and diameter 1 millimeter in water? And we're going to make an assumption that crude oil is so viscous that I can treat this as a little solid sphere. Okay. Viscous, whatever I wrote down here. That it can be treated as a solid sphere. Cool. So let's look at the friction factors. My friction factor, if I'm treating this as a solid, is this 4/3 GD over VT square, rho S minus rho F over rho F. And I'm taking this rho solid as 0.95. So I'm treating this little droplet as a solid. So that's my definition of friction factor. When I plug in the numbers, right, so it's going to be negative. So that means that it's actually a rising droplet. That's all. That's fine. So this is going to be negative when you plug in all of the numbers. 6.54 times 10 to the minus 4 meter square over S square divided by this VT square. So that's what my friction factor is in terms of that terminal velocity, but I don't know terminal velocity. Okay. If I look at what my Reynolds number is, d rho VT over mu, when I plug in all of the numbers, that comes down to rho F in this case, right? That comes down to 1,000 S over meter times VT. And we're gonna, do you mind if I just take 1 minute to finish this? You mind? Or you don't? I got you. Right. So, great. So now I'd like to, I have done all kinds of experiments, and I actually have the correlations between my F and my Reynolds number. We didn't actually derive it, but I showed you the graph. We can actually look into it right now. So technically, I know that my function, my friction factor is a function of Reynolds number. The problem that I don't know is that I don't know VT, so I don't know precisely what my Reynolds number is and what is the regime I'm in. Okay? So I could use F is F of Reynolds number, and we have graphs and formulas for that. But the problem is, like, I don't know Reynolds number because I don't know velocity. Velocity is what I'm looking for. So this is where I actually just go through possibilities and see which one fits. Okay? So I gotta go through possibilities. And find the match. So first one is laminar flow. And for sphere, Reynolds number has to be less than 1. And I didn't derive it for you, but if you plug in the Stokes formula and all that, you can actually get that for spheres, F is 24 over Reynolds. So this can be plugging in Stokes formula. So when I put that in, I'm gonna get, so I put minus 0.64 times 10 to the minus 4 divided by VT squared. And I also plug in this Reynolds number. That actually gives me, so I can take this and put it here, right? 6.54 is this number from, what, you can't read this? Come on. Yeah. So dot, 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 I can get that my VT is minus meter per second. But when I plug that VT into my Reynolds is about 27. But I assumed less than 1. That is not correct. Okay, so this and that don't match. So then you go to the other one. The other formula, and I didn't show it, but it's actually a nonlinear formula. I'm just going to quickly, I'm probably stopping everybody outside, but they're going to live with me now. So then my other option is turbulent flow. Uh, 1 to 6,000. Okay. In that case, F is square root of 24 over Reynolds. This is a fit to experiments squared. So Reynolds is a function of VT, and that has to be equal to over VT squared. And again, I can plug that in. I need MATLAB's F0 or something finding a root. Okay, so this is root of a nonlinear equation, like F0 in MATLAB. You need SciPy in Python and optimize in there. And dot, 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 when I get that, V infinity is 0.137, not infinity, but VT. And my Reynolds for that is 13.7, which matches the assumption. My assumption was that Reynolds was between 1 and 6,000. And that's the solution then. Okay. So again, this is why friction factors are useful, because I don't know flow regime. So I gotta go through cases. Okay. All right. See you on Monday. Stay dry.